Hello everyone, welcome back. Can't believe we're almost done the course. You know the saying, it gets worse before it gets better? It's about to get a lot worse, but then it'll get better because you're done and you're 1 or 3 credit hours. I don't know why credit hours work like that. 3 credit hours closer to a degree. So today, wish I could put these on learning outcomes, but basically, first I'm gonna actually set the right input on the projector. Booyah. Today we're gonna start by doing the rest of Thursday's lecture. The bulk of it was the debugging example that I gave, but there's a bit more stuff about information hiding that we gotta talk about. And then I'll ramble for an unspecified amount of time about term test results and assignment 3. And then we'll get started, possibly even finish, but I wouldn't bet on it, today's lecture. So, the way Thursday's lecture was supposed to end was us talking about static. In C, it means per file private, which is definitely different from what you know or how you've used static before. So basically, a static function or variable is only available in the file where it's declared. So this leans more into what we've been talking about writing safe code in a language that makes it really easy to write unsafe code. So for assignment 3 onward, any data or function that you deem private must be static. Because, as we'll see pretty soon, if something is not static, it's just sitting in the .c file, it's actually not so private and can be accessed at will. So let's see that in action. Don't worry about coding along. I'm going to mess up the string example again, so you probably shouldn't keep those modifications on your copies. Just watch and learn what not to do. I'm just going to check the main file or make file to see what implementation the main line uses. Oh, right, there are main list and main array. I'm just going to modify the list implementation arbitrarily. We could also do this on the array one. So check string. That is something that you'd think the user of this interface should not be able to access. They shouldn't even care about, they shouldn't even know it exists. And I'm going to modify it to print something. And then let's see where it might indirectly be called in the main file. So I'm pretty sure makeString calls the checkString function. So I'm going to put a print statement before that, just so we can draw a clean line between some stuff that we're doing that is evil and messy and times that we call the invariant function for legitimate reasons. Oh, of course. Let me fix that. Okay, so far, all's good, and it probably isn't clear what exactly I'm doing, but we could see check string gets called a bunch of times in our string implementation, but it's fine because main can't call that directly. Or can it? Wish I could make that Vsauce music start playing. I guess I'll have to move this up here. But that won't mess up what I want to demonstrate. We shouldn't be able to do this. I suppose checking the invariant of a ADT isn't really that harmful, but think of the implications. I'm calling a private function, and that's bad. This is probably going to mess up the compilation of the main array, but we stay silly. Yeah, whatever. The invariant check fails, and probably for good reason. I guess I didn't have to add that print statement. We already have clear evidence of the invariant check being called where it shouldn't be. And again, this isn't really about invariant checks, it's about private functions. I told you that any functions that were in the implementation but not the interface were private, and I lied. And now I'm going to unlie. Got to make this static. So now check string, both its declaration and definition, have the static modifier on them, which makes them per file private. Notice that when I first compiled it, I got the warning that there's an implicit declaration of the function check string. This means that the function check string was never declared in the main file or any of the files that the main file included. So it's telling us like, hey, this is dicey. But then the linker was able to figure out, oh, check string is in main list. Okay, I'll link it. But now that we have static on that function, look what happens now. Undefined reference to check string. And that's a non-starter. So might be difficult to see past the unrelated warnings, but when you make a function static, then it's finally private for real. Use static. The markers will get mad at you if you don't. Now, you might be wondering, maybe you have like completely innocent, legitimate reasons to share data between files. Well, you should know why you shouldn't do it. So it's bad design, basically. It exposes implementation details after I spent so long rambling about why you shouldn't do that. Basically, it'll make life difficult for any coders you're working with in the real world. And it also introduces high coupling. What's coupling? This is a sort of, or another part of the course that goes into what I would call pre-software engineering. You'll learn some principles for writing maintainable software that you'll elaborate on in the software engineering course, but you'll first get a taste of them here. So yeah, that was the rest of Thursday's lecture. Congratulations, hopefully now you'll be able to use a debugger and use static. So, what's next? Term test marks are going to be out soon. It's 96% graded. So the goal was to get it graded and returned to you by the VW date. We're on track for that. I just might have to talk to whoever the blue icon is. I won't hover over it to protect their privacy. But yeah, the term test is basically all marked. How do you think you did? That's rhetorical, don't answer that. Because the answer is about 75%. Great job. I think 70-ish is like the target average for a course beyond first year. If it was lower, I'd be concerned that you all aren't getting it. If it were higher, I'd be concerned that it's too easy. But 75-ish, keep doing what you're doing. And now let's talk about assignment 3, because it's out now and it's a doozy. Feel free to interrupt with questions as I go, of course, but I'm basically going to do the same thing that I did with the other assignments, scroll through the outline and comment on it. So you're finally done with bracket matching. Yay! Instead of bracket matching this time, we're going to look at memory management. That's one of the big things that separates the programmers from the computer scientists, understanding how memory works. And even if and when you get a job working in a program or a language that mostly manages it for you, it still pays to understand what's going on behind the scenes for the sake of writing efficient code and being able to fix things that go wrong. Actually, if you like the game Celeste, that was written in C#, which has a garbage collector for memory, and the developers talked about how they had to sort of work around C#'s memory management, which is supposed to be a no-brainer that you don't have to worry about. They had to work around it to prevent making too much garbage, because if the garbage collector were to run at an inopportune time, it could cause stutters and frame drops and mess up your 100% speed run. So where was I? Started talking about Celeste and forgot about the entire assignment. Right, we're doing memory management. You're going to implement something pretty similar to malloc, but using a different, thankfully simpler, allocation policy. Additionally, this is a memory management technique that you might end up using in the real world, which is to, rather than allocate memory just piece by piece, one allocation per object, you allocate like a huge chunk at once, and then once you're done with everything, free all the memory in that chunk. And during the program's execution, probably should have mentioned this earlier, you only allocate and free stuff within that chunk. This sort of makes your life easier with free, because you can actually afford to forget to free stuff without incurring a memory leak, as long as you remember to free the entire zone or the big chunk once you're done with it. So question 1 is just implementing the thing. You're going to get a header file, zones.h, that provides an interface for this memory management technique. It has functions like create zone, destroy zone, zalloc, zfree, and you just have to do that. Being able to work with memory just, I don't know whether to say more abstractly or more concretely, working as memory as the huge array of numbers that I described in class is pretty tricky. We will spend pretty significant class time going over how this is supposed to work. So don't be too intimidated. You should be plenty intimidated, because that'll help you work hard, but I'll be here to help, and I'll be talking about this assignment a lot. Rubric, I'm not going to go over this, but you should. This is I might have mentioned this before, but this is the exact same rubric that the markers use. So if you can go through it and identify that it follows all the guidelines here, like, oh yeah, my submission doesn't make the compiler print any warnings, stuff like that, then you're basically guaranteed to get full marks. Anyway, question 2 is to test your zones. So far it's kind of similar in structure to the second assignment. You make a thing and then you test it. You might want to do questions 1 and 2 concurrently. This is a thing you'll learn about in software engineering, but it's called test-driven development. You just write your test first. They will all fail because there's nothing to test. But then you write your implementation according to the tests. And then if you wrote a thorough enough test suite, then you'll be done the implementation once all your tests pass. That's one way to do it. You can also just write the whole thing and then test it. That's fine. So there's not actually that much to talk about here. You've written a test harness before. You're more than welcome to reuse the structure of your test harness, or even mine. The sample solution to assignment 2 will be posted in the next couple days. So yeah, test general cases, test edge cases. And then I'm going to test your memory manager. There are a bunch of extra test cases that I'm going to release next week. The reason for that is, I guess, to avoid test-driven development using my tests. it's going to be released pretty close to the due date, so you won't be able to just take my tests and then start working on your tests and your implementation. You won't have enough time. The idea is that you make your own implementation, and then hopefully you're able to just not rubber stamp it, but just check that it works against my test suite, which is pretty thorough. And remember me waffling about release builds? It's finally becoming important because some of the tests will actually work on your code in release form, which is just a matter of passing the dn-debug flag into the clang command. This will make assertions not work. It'll just skip them. As such, you need to make sure that your code works both with and without design by contract. And this is a good idea in general because while you're developing, you want errors like this to be pointed out loud and clear. It should crash so that you know that something is wrong. But when it's in release form, if something goes wrong, it should just do its best to handle that error because no one likes a crashing program. You've probably applied a similar methodology to exceptions in languages that have those. During development, it's useful to have your programs crash with an exception message, but in production, you should have try and accept blocks that anticipate exceptions that can happen and then handle them by changing the program's flow or most likely displaying an error message that won't make non-tech savvy users think that they're getting hacked. So if you're really good at making zone-based memory managers, question 3 won't actually be any work. But if you're anything like me, when I did this assignment so that I made sure that I knew what I was talking about when I tell you all to do the assignment, question 3 is going to expose a bunch of flaws in your implementation, and you're going to have to do some debugging. Good luck. And then submitting your assignment, it's as normal. Use Handon. Include all the things I tell you to include. Run the command. You got this. So this is all new information, and you do well to give yourself time to just sort of process it and crunch it up. But are there any questions right off the bat about the assignment? I'll give 30 seconds or so. Oh, I'll completely shut the door while I'm waiting.
Would you say this assignment is going to take longer than assignment?
Yeah. A memory manager is more complicated than a stack. So, actually, maybe not. Wait, I'm just gonna make sure the mic is in my pocket and stuff before I keep talking. So in assignment 2, you had to do stack, the test for the stack, and an application of the stack. This time, you're still doing implementation and testing, but no application. So while the implementation and testing is going to be a lot more complicated than the equivalent for the stack, it might end up being about the same amount of work due to the lack of an application question. But still, start early, be intimidated for the sake of making yourself work hard, blah, blah, blah. Well, now that we've gone over all that stuff, I think we can start today's lecture. Crazy. Was it this one? Nope. Is it this one? Probably. Yep, it's July 29th. So there's a file called void.c. It's on the course website, and it's going to be a taste of, memory management. Because we're going to have to work on a level more low level, as in close to the hardware, than what we've been doing with having an actual type system. I've alluded to this before, but everything's a number. And numbers can be interpreted as integers, as floats, as characters, but when you get down to it, it's all ones and zeros. So by the end of today's lecture, which might spill into tomorrow, you should be able to describe concepts of memory management. There are a few that are looked at in this course, but a couple that are more relevant to this lecture. First fit memory allocation is the memory allocation policy that will be used in assignment 3. It's different from the policy that Malloc uses. I'll elaborate later. And of course, the heap. Malloc just worked because of the beauty of separating interface from implementation. But now that you're actually implementing memory management, you're going to have to get your hands dirty and learn how the heap works. So we need to talk about void pointers. So as you know, arrays are addresses, and pointers are variables where the value is an address. So assignment 2, you took int pointers to the peek and pop functions, and those were memory addresses to where an int is stored. And pointers like that had a type. An int pointer knows that whatever memory it's pointing to contains an int. Same with chart pointers and even pointers to structs and whatever else you might point to. A void pointer throws that bit of information away. It's a typeless address. It's just an address. It points somewhere in memory, and you have no idea what it's pointing to. And you've been using them for a while. Malloc returns a void pointer. In hindsight, this should make sense because of how we've been separating interface from implementation. With something like the string example, or even the stacks from your assignment, the main function, main program, doesn't have any information about the structs you're using. So when you allocate space for it, it returns a void pointer. So it's just a memory location. You don't have to share any implementation details in order to use it. So when you do this, Malloc returns an address where that size number of bytes have been allocated on the heap. So I'm going to basically draw that picture of our memory model again, kind of to jog your memory. Should be clear enough. Let me know if anyone can't read it. So, this much will be a review basically. A program's memory has a code section, the runtime stack, which grows and shrinks as you call functions, and a big ol' heap. So say we have a function that has a call to malloc in it. Say so the main function will have a stack frame, as you know. And it has space for the local variable pointer and a bunch of other stuff like return address that we don't need to go over again. The heap is still worth thinking about as a gigantic array. Just one array that's as large as your computer has RAM. And as you'll learn in computer organization, probably a lot more because of swap space. I guess that's more of an operating system thing. Whatever. So we could have addresses. I'll just make it start at 0 for simplicity. When you call malloc, it allocates some, or that amount of space somewhere on the heap. How does it choose where to put your 1024 bytes? That's going to be a mystery for now, but it'll be a mystery that I'll partially solve during the lecture, and then you'll solve it completely on the assignment. wake up. And now let's see how we can get pretty silly with this concept. I'm pretty sure I put this on Aviary somewhere. Void example. Again, don't worry about typing along. I put void.c on the course website because, well, it's not really demonstrating any techniques. We're not going to go through it line by line, but it does show off some stuff you'll need to know for assignment 3. So in void.c, we have a struct that has a few variables of different types. We're just going to ignore these buffer functions for now. And then it allocates, using malloc, a big buffer, so a big array basically, fills it, and then by some nebulous process, processes it, and then frees it. So how does it fill? It actually just writes the string hi to memory over and over. So I think I'll visualize this on another piece of paper. So this is some address of memory. We have no idea where because we don't need to worry about how malloc works. But you don't have to worry about this exact indexing. All you need to know is that it writes hi over and over again for the entire buffer. And on and on and on. I'm hesitant to actually demonstrate this because my mechanical pencil appears to be out of lead. Let me try and fix that real quick. Cool. So it's actually copying HI end of string character, and then internal plus equals 2. So it moves the start of the string. And then now the position to write to is the position of the null byte, so it overwrites that with the next high. So that just goes on and on and on for however large the buffer size constant is.
So it's happening in heap.
Yes. So
How? Like there's no malloc.
malloc takes place in the main function. So on line 40 of void.c, we allocate some space on the heap. So then everything else takes place on the heap. And then this is where it gets kind of funky. in process buffer, it just interprets that garbage data that are all those repeated highs as data structs. And we can do that because everything's a number. Not even letters are safe. So it casts the buffer into a data pointer, which basically makes it take the array of just whatever memory, literally whatever memory, and interpret that as an array of data structs, and then just print out each data struct. So what the heck is this going to print? Probably didn't need to do that. I have it right there, but yeah, you get a small Clang review. Oh, crap. Thanks for that. Did I say anything important? Yeah, kinda. Here's where it casts the buffer to a data pointer, which makes it interpret whatever memory is in the buffer as an array of data structs. And then it goes through each data struct and prints its properties. So it's going to somehow interpret the garbage data, all those highs, as something. And here's something. These are all of the data structs. So a certain amount of highs, I believe 4 of them, because ints are 32 bits and chars are 8 bits. So this number is actually like high, or something similar to that. Don't take my word for it quite yet, because I'm going to use the calculator to make sure. And then you'll learn, or have learned, how floating point variables are represented in Comp 2080. But the garbage data, the bits in all those repeated highs, turns out to be this floating point value. And then you may remember the data struct contained an int, a float, and a string. So luckily it actually interprets the rest of the buffer as a string. And since we overwrote all those end of string characters, it interprets the rest of the buffer as that string. And you can see each data struct has a smaller and smaller buffer, or a shorter and shorter string, I should say, because it's closing in on the end of the buffer. Whatever happened to lie beyond that is thankfully 0, so it interprets that as an end of string character. So let's see, pretty big number. Cool. So this number isn't quite high, but it seems that there may be something at play called padding, which I'll probably talk about later, which is basically something that the compiler does to make everything fit into memory nicely. Parts of a struct might not be directly next to each other, as you might expect. And just to elaborate on that, this number is high thing. So down here is the binary representation of the number. And each 8 bits is a char, and each 32 bits is an int. So since our number/string thingamabobber ends with H, we know that these bytes, or this byte, these bits, form the ASCII value for H. We can just verify that real quick. $104 in decimal. That. Okay, cool. By observation, these last 8 bits didn't change when I pasted in the big number. So we can be assured that, yeah, these 8 bits are the char H. And then, of course, these 8 bits are the char I, these 8 H again, these I again. So yeah, everything's a number, and every number is either a 1 or a 0. We wrote some garbage data into the heap, and it's being interpreted differently based on what we say that it points to, what type we say that it points to. Assignment 3, we talked about this. It's fun. So we're going to, I guess I didn't need to dismiss this out of hand. We already looked at the assignment outline, but now I'm going to give a bit of guidance on how exactly to solve the problem. So we need some ground rules, and we need to figure out what the memory manager needs to know to manage memory. So first of all, our memory manager is responsible for all memory management. This zones technique, where you don't actually have to worry about freeing memory that much because you can free your memory all at once at the end, it only really works if you only use that. If some doofus on your team is using malloc instead, then it kind of ruins the whole thing because memory leaks are once again possible. So I think I elaborate on this in the assignment outline, but you're basically only allowed to use malloc, I think exactly twice in your solution. Once to allocate all the memory for your zone, and then in another part of the code, that'll become a bit clearer later. Basically keeping track of metadata for the allocations you're making. Excuse me. So what does your memory need to know about the memory it manages? It needs to know what memory the client has allocated, memory that they have not allocated, and that's equivalent to deallocating the memory, and what to destroy when the manager is destroyed. So this may or may not be similar at all to how malloc does it. I don't know how malloc does it. I know how our thing is going to do it, though. So a client will call our function zalloc, to allocate memory within the zone. And then we will keep track of the references we've given out. Zalloc will return a void pointer just like malloc, which the client can do whatever with. But we're going to also keep track of those pointers, and I might be getting ahead of the slides here, as well as how large the allocations that those pointers correspond to are. So malloc applies a free space management policy. I think this just goes to Wikipedia. Oh no, it's a textbook. Yay. You absolutely don't have to read this. Don't worry about it. But if you're taking operating systems instead of distributed computing, do it. It's so fun. I guess you could study ahead. There are different free space management policies, and malloc uses best fit. Best fit takes a memory allocation and then finds the chunk of free space that is closest to the size of the allocation you want. If you really want to, you could look at the malloc source code and figure out exactly how. But again, it's totally optional. You know some open source code is getting good where it's basically just all comments and macros. Oh wow, an if statement, that's crazy. Oh, this one's static. Yeah, whatever, we don't need to understand this. I'm going to draw a bit of stuff for allocation policies. So say I have a heap, the heap, and it looks sort of like this. We're not going to draw lines between bytes of memory. We're looking at this at a slightly higher level. Let's say some stuff over here is used up. It's been allocated by some process. Then there's some free space here. And then another allocation. And another free space. To best illustrate what I want to show, it would actually be better if the big free space was there first. So pretend I drew it like that. So say we want to allocate a chunk of memory that's this big. The best fit algorithm, by the way, you won't have to implement this, but you may or may not have to know what it does for the final. The best fit policy finds the region of free memory that is closest in size to what we're allocating, which is this one. I'm just going to label this. Best fit puts it here. Probably getting ahead of myself again, but our assignment 3 memory management solution is going to use, thankfully, very thankfully, a simpler algorithm called first fit, which just puts or allocates the memory just at the first memory location in which it'll fit, such as right here. Yeah. I'm just eyeballing how big that square was. But despite the botched arrow, you could probably see how first fit will put it at the first large enough free space it finds, while best fit puts it at the best free space that it finds, the free space that is closest in size to the thing you want to allocate. What makes best fit so best, you ask? Well, that goes to an issue called fragmentation, which is an issue of having just a whole bunch of little tiny bits of free space that you can't actually allocate stuff into. From this example, you might think that first fit decreases fragmentation the most, but that's only because I had a huge chunk of free space first. Best fit helps ensure that stuff is put where it, keep saying these words, fits best. And basically ensures a nice layout in order to reduce fragmentation. Also, side note, there's a process called defragmentation, which takes memory that is probably pretty fragmented and moves it all to the front of memory so that it's all packed together, and then there's a huge chunk of free space at the end. When I took 2160, the final assignment was to implement a defragmentation algorithm. So very similar pointer shenanigans to your third assignment, but sort of a different focus. So that's the end of this lecture. We have 15 minutes left, so I think I'm going to get started on the next one. The more information you have about assignment 3 early, the better. And as we talked about at the very beginning of the course, I'm exactly on pace with the lesson plans now, but if I'm persistently a lecture or two ahead, you guys will get a free day at the end of the term. More time to study, I guess.
Final will be on 14th, right?
Yes. Actually, excellent diversion. Not a diversion, distraction. There's a link you can go to find your the final exam schedule. I personally find this much nicer than going to Aurora. And it's here. I think other browsers don't have quite as nice prediction as Safari when trying to figure out what you're trying to find, but you could probably Google University of Manitoba final exam schedule to get it. So, Comp 2160, right there. Yeah, so it is the 14th. I didn't want to say, yes, it's definitely the 14th from memory because I could have gotten that wrong. But yeah, it's on the 14th at 6 p.m.
And last day of class?
Last day of classes is the 9th, I think. Yeah, right there. So anything between that, between the 9th and the 14th will be final exam studying time. And compared to the pace that we've been going on the rest of this condensed course, that's downright luxurious. So study hard, I guess. Wow, time flies when you're having fun. Welcome to July 30th, 2024. Today, we're going to using zones. I haven't set that up. I might just end this lecture if we get to anything that needs that code. But by the end of tomorrow's lecture, you should be able to talk about memory management, specifically first fit memory allocation. Also, we're going to be talking about more pre-software engineering stuff that I sort of hinted at by talking about how sharing data directly between files leads to high coupling. We're going to actually talk about what coupling is and talk about a related concept called cohesion. I might have just explained this. Best fit, worst fit, next fit, first fit. Kind of sounds like a Dr. Seuss rhyme. And your zone-based memory manager is going to use first fit. And this is probably a nicer definition than any drawing I could make. First fit allocation policy. Given a chunk of memory and allocation metadata about that memory, do a linear search to find the first unallocated space big enough to satisfy the request. This was nice and simple on the drawing. The first unallocated space big enough to satisfy the request was right at the beginning of the heap. But you could imagine having some used up space at the start. So it would do a linear search, which is perhaps the most intuitive searching algorithm. Just start at the beginning and move along the thing you're searching until you get to what you're searching for. Just move along until you find free space. No, I can't using zones. We'll do this tomorrow. Basically, there is a file that I have that's similar to using stack from the second assignment, and it just provides a usage example for using the zones interface, and can probably help you on the test. No, not the test. The tests. It'll help you write tests. Oh yeah, it's more static stuff. So if you want to share data between files, you could use something like this in Java. Imagine that these classes are in separate files, as they should be. So second has a function that modifies first.counter. Pretty nice stuff so far. How do you do it in C? Imagine that we want to have a scheme like this, where file1.c has some sort of counter, and then file2.c is able to read and write to it. Again, how do you do it? With extern. So first, in the first file, you declare and define the thing you want to share. Also, this should be raising red flags all over the place. I'm showing you how to do this in order to justify why you shouldn't. So then when you want to do something illegal and evil and bad, you declare that thing again without defining it and use the extern modifier, saying that thing counter is external to file2.c. And then from there, the linker will do its thing. It'll know that thing counter in file2.c exists somewhere else. Eventually, it'll find thing counter in file1.c and link them. Don't do this. Why not? Bad design. Exposes implementation details. You heard this earlier in the lecture. High coupling. I promise I'll justify this eventually. So, yeah, please don't use extern. This little bit was basically to preempt anyone who thinks it's a good idea to use extern on their assignments. You might think it's useful to share data directly between files, but in the vast majority of cases, it's not, because of this fancy buzzword that I'll explain in the next lecture. But you could probably already begin to think about why this is the case. We've been talking about separating interface and implementation for a whole bunch of classes now. And when you start working on really big projects, whether they're group projects in later courses or making stuff in the real world, jeez. Wonder if those intermittent buzzes help people pay attention, like falling asleep and then. Anyway, I'm kind of stalling for time here. Extern is bad. What was I saying about interface and implementation? Yeah, the less that bits of your code know about each other, the better, because when different parts of your code know as little as possible, then it's easy to change those parts of your code, because those other things that don't know as much thus don't depend on any specific details of your parts of the code, i.e. modules from modular design. So tomorrow we'll go into more pre-software engineering. Basically, I'll say a more polished version of the rant that I just gave, and we'll explore using zones. I highly recommend looking at the assignment outline tonight, but you might not want to start it until you've seen this usage example. And yeah, pre-software engineering and using zones is up tomorrow. And I'll get the term test marks out by the VW date.
Today?
Tomorrow. Well, I'll get it out by tomorrow. Really, it was supposed to be out today, but that one question isn't fully marked yet, so I need to figure out what's going on and solve whatever problem is in the way of the markers doing the complete job. Don't worry about it. I'll get the midterm marks out as soon as possible. And that's it. Get out of here.